Hello everyone, I'm Chieko Kuji with Tohoku University, Japan. Today I'm going to talk about relationship between unrelated amorphous alloys microstructures and microregion structure properties and that influence for machinability. This is today's overview. Then I will talk about the background. The left figure shows a breakdown of domestic electricity consumption in Japan. From this figure, we can see that more than the half of the energy is used for motors. Furthermore, 33.5% of the energy is lost due to energy conversion losses. The motor is configured with various parts, but the performance of the motor depends on the soft magnetic materials property, which is used in the motor core. Since the development of silicon steel in 1900s, various soft magnetic materials have been developed. Among these materials, I have focused on the Fe-based amorphous alloys, which have high soft magnetic properties, high strength and toughness, and high corrosion resistance. Here, I compare the soft magnetic properties of silicon steel, which is currently the most commonly used motor core materials, and iron silicon boron-based amorphous alloys. The energy loss due to energy conversion is 1/10 that of non-oriented silicon steel seeds. This indicates that it is a very excellent soft magnetic materials. Let me briefly explain amorphous alloys. When cooled from a high temperature molten state, general metallic materials form crystals and solidify. On the other hand, when cooled very rapidly, crystal nucleation and growth are suppressed, and the materials remain in a liquid state below the crystallization temperature. Then, when it reaches the glass transition temperature, it solidifies while maintaining a random structure like that of the liquid state. Such alloy metals with a random structure are called amorphous alloys. Unlike ordinary crystalline metals, amorphous alloys have a random structure. Therefore, there is no magnetic anisotropy and no pinning effect caused by grain boundaries, and the eddy current loss is also low because the material is very thin. For machining such thin materials, blanking is often used. In the blanking, a pair of punch and die is used to cut the materials, and the material is broken by the propagation of cracks generated by the compressive force from the tools. This is a schematic diagram of the fracture surface of the blanking. First, shear drop is generated by shear deformation, and next, sheared face is created by friction with the tool. And when the material yields, A broken face appeared due to the propagation of cracks and machining defects such as burrs appeared on the bottom surface. Amorphous alloys have high strength and toughness. This property causes excessive shear droop and severe tool wear. Next, I considered a way to overcome these difficulties in machining. When amorphous alloys are heated, the random structure changes through the rearrangement of atoms and nucleation and growth, and finally changes to the crystalline structure. As the structure changes, the mechanical properties also change. So I thought, if structure change like crystallization reduce strength and toughness, wouldn't it be possible to reduce machining resistance? And also I thought that changing the whole structure will cause a worsening of soft magnetic properties and changing in product strength. So we have proposed a new machining method that improves machining performance while maintaining product performance by summary modifying only a few micrometers of the materials to a suitable structure for machining. Therefore, it is crucial to understand the influence of the microstructure of the microregions involving in the machining process on the mechanical properties. These are the objectives of this study. In this study, the following investigations were conducted on Fe-based amorphous alloys as a fundamental study for the development of new machining method. So we evaluated the sample which were homogeneously annealed in order to discover a structure that is suitable for machining. First, we investigated the microstructural changes caused by thermal effect. Next, microtensor tests were conducted to clarify the relationship between microstructure and mechanical properties in the microregions. Finally, branching tests were performed to evaluate branching resistance and quality. Let me now move on to explain the results of the experiment. First, we tried to create different microstructures in the amorphous alloys. We used Fe-based amorphous alloys for the experimental material. Amorphous alloy changes the microstructure sensitively to temperature. Therefore, in this experiment, we used a DSC apparatus for heat treatment. DSC is a thermal analyzer enabling precise temperature control. The sample was cut into pieces 3 mm wide and 5 mm long and set it in an aluminum pan like this. For heat treatment, the heating rate was set at 20 Kelvin per minute and the sample was cooled to the room temperature at the cooling rate of 20 Kelvin per minute, without holding it assembly at the maximum temperature. Structural analysis of the heated sample was performed using XRT and temp observation. Left figure shows the results of XRD analysis and the right figure shows the result of thermal observation. The amount of crystal precipitation gradually increased as the heating temperature increased. It was found that the iron 3 boron was precipitated at the initial crystal, followed by the formation of core shell-shaped composite crystals, and finally it was completely crystallized. Now, I next performed microtensor tests on amorphous alloys heat-treated to various structures, and we investigated the effect of microstructure on the mechanical properties in the microregion. In this study, we performed microtensor tests in the FIB apparatus. In this method, tensor properties are evaluated by applying the both ends fixed beam problem based on linear elastostatics. In this experimental procedure, a probe, a microtensor sample, and second both fixed beam are fabricated in the FIB apparatus, and then each element is bonded by tungsten deposition. The sample will form to a radius of 0.5 to 1 micrometers and a length of about 5 micrometers. Next, the probe was put up toward the tensile direction until the sample was broken. Movies were taken during the test, and the amount of diffraction of the beam and the elongation of the sample was measured from the snapshot of the movies to obtain the stress strain curves. Here is an example of the snapshot obtained in the microtensor test movie. From the captured image, the length of the specimen and diffraction of the beam during the tensor test are measured. Stress and strain can be obtained from these formula. I will show you a test movie. This is a tensor test movie of an other shaped specimen. This specimen slipped and fractured at an oblique angle below localized shear deformation. This is typical fracture behavior of amorphous alloys. These are the stress strain diagrams for all samples. The vertical axis shows tensile strength and the area under the stress strain curve shows toughness. Strength and toughness decrease with increasing structural relaxation and precipitated crystals. On the other hand, when fully crystallized, crystalline plastic deformation increased and the strength and toughness increased again. Furthermore, we observed the fracture surface of each specimen. Specimen exhibit a microstructure dependent fracture shape. To summarize the experimental results so far, the amorphous are fractured in the elastic range under condition of structural relaxation and the beginning of crystallization. And the tensile strength was reduced the most in the composite crystals, sparsely precipitated states. And plastic deformation occurred with increasing crystal precipitation. And strength and toughness increased again when the amorphous alloy was fully crystallized. Finally, the inference case of the mechanical property of the microregion on masonry was investigated. In this experiment, Franklin tests were performed on the sample whose microstructure and mechanical property had just been evaluated. We measured the masoning resistance and evaluated the masoning quality. The left figure shows the relationship between heat treatment temperature and masoning resistance. For the received specimens with high strength and toughness, masoning resistance was higher due to friction with the tool. By decreasing the strength and toughness through heat treatment, the masoning resistance was significantly reduced. On the other hand, the masoning resistance increased again when the plastic deformation ability increased. This indicates that the reduction in strength and toughness due to heat treatment dramatically reduced masoning resistance, while plastic deformation contributes to the increase in masoning resistance. The left figure is the same image of the machined edge observed from the backside. Excessive shear droop appeared on the adhesive specimen with high strength and toughness, and porous appears on the fully crystallized specimen. In other words, it is clear that the machining quality improves in the middle structure of crystallization. Finally, we summarize this study. In this study, we investigated the effect of thermal microstructure changes on the mechanical property and masonability of amorphous alloys. We found that mechanical properties strongly depend on microstructure change. The tensile strength of the amorphous alloys drop it down due to the change in the microstructure. And masoning resistance and quality are most improved when fine crystals are sparsely precipitated in the amorphous phase. If you are interested in today's presentation, I hope you will read my paper via these QR codes. Thank you very much for your attention.